Hi, everyone. I'll try not to keep this too long so that we can go and eat lunch super fast. So here, I'm going to talk about how you could build a bank using Go. So my name is Matt. I'm kind of a distributed systems engineer. I've been programming Go for about 3 years now. And I work at a company called Mondo. And Mondo, we are building a new kind of bank. So from my perspective, banks are kind of stuck in this kind of age. Banks seem to want me to go to branches. The online experience is terrible. And this isn't really kind of the experience I should have in 2015. But there's a lot of reasons for this. A long time ago, when we started turning records into electronic records, obviously we had things like mainframes. And we have these centralized ledgers of all movements of money. And these things have grown. And then through the 80s and 90s, there was lots of IT outsourcing. And largely, banks have seen this, have thought of tech as a cost rather than an advantage. To put this in perspective, Barclays spent approximately £3 billion on tech last year. And just put that into perspective, what could you build for £3 billion? Especially if someone gave you £3 billion every single year. That's insane. And fundamentally, these systems are monolithic. And it doesn't really matter how many things you apply around the outside. If you build really sweet web services around the outside, fundamentally, the movements of money are trapped in these huge monolithic systems that are nearly impossible to migrate away from. So in 2015, this really shouldn't be the case. Everyone does everything on the mobile. And everyone expects to do everything on the mobile. I actually can't really log into my banking app. It just doesn't work most of the time. Or I press on my balance and I get a message saying, service not currently available. How hard is it to show me essentially an integer with a little bit of formatting? It's really not that hard. And this is quite a common thing. So you can have a little peruse on Twitter. So this is a great example from early this month. Standard kind of experience, people can't do something like phone, doesn't work on the website. You have to either go into a branch or phone some customer support line. And usually if you go into a branch in the UK, you actually get funneled over to a phone where you phone the same people that you could have done from home. And again, this is a recurring thing. So it really doesn't matter which bank you go with in the UK. They're basically all the same. They provide the same level of service. There's no competition really in the market for current accounts. So could we do something maybe a little bit better? If we started from scratch, if we built our own technology stack from the ground up, using technologies that are current, and built them in a way that we could continue to develop them and use tech as an advantage rather than some necessary cost of doing business. So that's what we're trying to do at Mondo. We're specifically mobile first. We are currently in the application stage to apply to become a full bank in the UK, which means we have all the same guarantees that any other bank provides. We keep your money safe. And fundamentally, we want to provide more than that. We shouldn't just be a bank statement, which is a list of things that happened. We should be able to provide insight into what's happened. And actually analyze your data and predict if you are going to go into financial difficulties and provide tools to help people with them. So as an example, this is my app from yesterday. I can see my things and I can do a search. It's really not very hard. I'm literally searching through a list of things. I could probably also show some extremely basic stuff. And given my card, I don't know if anyone's lost their card here. Yeah, probably someone. I have a habit of losing my card and then finding it about a day later, at which point I've had to phone up, cancel it, and then wait 7 days for a replacement. It would be quite easy to change an active flag in a database to false, and then potentially change it back to true when I find it. That should be quite simple to do. So these are the kind of things that you could build if you built a bank from scratch. And we've started about 6 months ago. and we have working debit cards, and we'll be launching a beta in probably October. But there are some challenges with this. One notable one is if you want contextual information, something like the amount you spent today, that's actually not accurate for 48 hours because cards don't settle through the payment networks for that amount of time. So we have an indication of how much money is spent, but it's not quite confirmed. Also, where you spent that money is a bit interesting. That data doesn't really exist in financial networks. So if we want to display maybe a sushi, when I go and buy some sushi on my push notification, we have to build that data set ourselves, and we have to augment it with things like Foursquare and Google Places, and then try and hook those up to essentially an 18-character string that we get off a payment network. And it's not just card networks that have these limitations. For anyone who likes Monty Python, this is an 18-character string. You should be able to send that as a payment reference if you're transferring money between people. Except in the UK, and in fact all of Europe, the O with a line through, a straight through, is not a valid character. And bank networks substitute that for O's. Or if you were, say, Turkish, substituting I's without dots for I's with dots, in this case actually caused 3 people to go to prison. And emojis are just not even a thing. So if we're going to start with a mobile-first application, we'll probably have an application. What we didn't want to do at Mondo was just build some huge thing. So the standard thing would be, as a startup, you build a very small application, it gets a bit bigger. Maybe you kind of add some more databases, some search, maybe some caching, integrations for everything, and you've got like this huge application, which obviously is something we will all worship for eternity, and none of us want at all. So there's clearly a lot of better ways, and breaking these applications apart into microservices is a very common trend at the moment. And if you're starting from scratch, that's a great place to be. You want to be able to move quickly, but if you could build your applications in a very scalable way, in lots of extremely small components, then you're at a great starting point. You can move with the market. And these things can just communicate however they need to, sometimes synchronously, sometimes asynchronously, be event-driven. And we're writing all of this in Go. So our basis for building each one of these is that every service needs to have a single responsibility. Everything should really only do one thing, do it extremely well, be very focused. And that means we can keep our applications to a few hundred lines of code. Beyond that, they should also be specifically orientated around areas of our business, so they're extremely easy to understand. And developers can then come along who haven't worked on these projects and actually be able to get up to speed and add features extremely quickly around functions of our business. And although we have a very small team at the moment, that's something that we need to think about, because although there's always a trade-off of technical debt in the future, we want to be able to move extremely quickly. And having small services that arguably we could delete and replace with better functionality is something we want to be able to do from day one. On top of that, we need extremely well-defined interfaces. So we actually use protocol buffers, which gives us a very nicely defined file which defines our interface. It's strongly typed, and we get automatically generated structs using the protobuf generator. And then composability, which you can think of if you've orientated your services around specific business functions, you might have, say, a service that sends text messages, which means if you then want to build a completely different feature that needs to send text messages, your work's half done. You can just quickly knock up a piece of code, deploy it somewhere, and your development process is much quicker. So starting right from the beginning, we're obviously going to have a load balancer. We will have some HTTP API. We can obviously just use Go's built-in serve muxes, and then some form of transport that's going to transport our messages to and from services. And we might have n number of services, and they'll probably all have their own databases, and then we can scale this by applying this pretty much in a box and deploy it to multiple availability zones and multiple data centers. So how does Go fit into this? Sorry for the brief introduction. So if you start today, there are thankfully quite a number of ways that you can start building microservice architectures. So there's a few examples. Peter will be doing a talk on GoKit later. And then we've got things like Kite, GoMicro, and gRPC, which has come out of Google and Stripe. And these all provide like frameworks or RPC frameworks to deal with the extremely low-level passing messages between all of our services. And ideally, we can then offload most of that, and we can get on with writing decent business logic that ultimately drives our business forward. Unfortunately, or fortunately for us, we're not really in the tech business as such. We're building a bank. So our focus is to literally build something as quickly as possible that is reliable enough that we're not going to lose people's money. So we have our own versions, which are open source. They're MIT licensed. And we have two main libraries. One's called Typhon. This is a very low-level RPC transport, which will deal with sending messages to and from a client and server through some form of transport. And then on top of that, we layer another set of libraries which build out clients and servers and allow us to build services with a very small amount of code. So we have another library, Mercury, which we can, with a few lines of code, initialize a server. We can add a few handlers into this, and that is a deployable block that we can put somewhere, and we can easily communicate between our services. And then from that, we can start building out things like a login API, where we would, say, take in a specific JSON message, we'll decompose it, and then send it on to the other components, perhaps an authentication or permission services, which can then handle all of our like nitty-gritty work. Now with HTTP2, we'll be able to also then aggregate a huge number of different requests that we need. And for anyone who's worked on mobile apps, you usually find that because the latency is high, you need to make your API responses much snappier, and it's much easier to actually aggregate as much information as possible into each individual network call. So we can potentially do things like aggregate our account response, where when you log in, we'll actually look up your account details and we'll return that to the app as well. Or if you log in, we want to actually show you a whole feed of events that's happened, and we can aggregate that and send that back to you. But what do I actually mean when I say one of these services? So for us, a service is a Go binary that's really composed of three different things. There's some handler that's right at the top level, and that is going to be dealing with taking messages on and off a transport, dealing with responses, enough to abstract away that from our core business logic, so that if I'm just like knocking up a quick thing, I don't really need to deal with the top section. I can just write some core logic. And I probably need to store some data somewhere. Most apps are pretty much just marshalling JSON into a database and then back out, and ours is no different really. In which case we need some way of easily accessing storage. So in our case, we're using our Mercury library for this, and then we have a number of libraries which are abstracted and automatically configure themselves so that I don't need to deal with like the IP addresses of databases and what the database names are. So onto some code. This is literally from one of our services. This is the main.go file. There's some imports that I've neglected to mention. And we're really doing three things here. We're initializing a service, and we need some configuration. So we probably need some kind of routing key, which the transport will use to register this service to receive and respond to messages. I've snipped the description for brevity. That would actually be a fairly long description of what the service does. And then things like service discovery can pick these up automatically, and we can build those into dashboards. And then we're going to add a number of endpoints, which is where really our core functionality. And at the end, we're going to run our server, which will connect to our transport and start sending messages to and from. So our server interface is very simple. We have a name, and then we have the ability to add and remove endpoints. And an endpoint is very simple. It's pretty much a handler function. We also have being able to start and stop and run, where we pass in a transport, and by default we pre-configure these, so I don't really need to worry about this. And we also have configurable middlewares, actually both on client and server, though this is just the server middleware. And I'll come on to why we need these in a sec. Obviously, Matt talked about a middleware in the last talk in here. So in our case, we want to first add a couple of endpoints. And an endpoint is going to be an extremely basic struct. So we literally have a handler, which is a function that takes a request and returns a response and an error. And we also have a request and response interfaces. Now, we can actually leave those blank, but the cool thing is, if we provide those as a struct, then we can do automatic marshalling. So we use protobuf all the way through for everything, so we can actually define our interface as a specific protobuf request object, and then a protobuf response, which may have nested types within it. And then when we handle this function, my handler will automatically have had that unmarshaled, so I just need to typecast it. And I can just pull the body out as an already unmarshaled object. And then within my handler, I can literally do anything I want. So I'm probably, in a lot of cases, going to be calling other services to do other things for me, or I'm going to be writing to a database, or really doing anything. And then once we've added our endpoints, we're then going to run our server, which is going to use our transport. So transports, in this particular case, is a really good example of how we can use the power of interfaces in Go. So in our case, we have a particular transport implementation that's in our Typhon library, which uses AMQP. But we can also implement a mock interface. So if we're doing all our tests, we don't really want to spin up any of our infrastructure, but we can still model messages going between any number of services because we can just do an in-memory message bus. So a transport interface would literally be listen for things, stop listening for things, respond, and send. So if we're going to send a request, we probably need to then be able to respond to incoming ones, which we receive from listening. And we also get a ready channel. So we can fire off our server, and then we can sit waiting on the returned channel from ready. And once our transport's connected, we'll close that channel, and all the Go routines waiting for the transport can continue executing. At which point we can use our channel that's returned from listening, and we can just range over this channel and fire a new Go routine for every inbound message. And that's like super simple. That means within a few lines of code, we can fire up a connection to AMQP. I can have registered a particular protobuf, and I execute a function when I receive that. And that means that I can build services and deploy them in like an hour, or well, probably a lot less. So when we're building these, we're probably going to have some form of API. We're going to receive a message off that on HTTP. We're going to decode that, use our client to send a message on, and then that's going to go, say, to our customer API, which handles that particular section. And in that, we're going to unmarshal various JSON things, decide what behavior we need for this, and then fire on a sub request to our customer service, which might pull out specific customer data. So that works quite well if you are sending extremely vanilla messages. But realistically, to do more interesting things, we need to be able to wrap these in some form of middleware. And a good example would be being able to trace messages through. If you're using Zipkin or some other distributed tracing mechanism, you need some way of marshalling like identifiers of this particular request as it goes through 3 or 20 different services. And you can do that using middleware. And if you pre-configure your middleware, then I, again, don't need to worry about this. So I can fire up a service, and this stuff is just dealt with automatically. And we can literally, for every client request that goes out, we'll execute a particular interface that has a request and returns the request, which is then passed on to the next middleware in chain. And when we get a response, we will again pass in the response. We'll actually pass in the previous context. And in this case, actually, our requests are also implementing the context interface, which is useful if you need to be able to store arbitrary information within a context of a request. So I don't know if anyone's used the context library here. No, yes, one or two people. So context is fantastic for being able to just dump extra data into requests. And as long as you propagate that particular context through every function call, you can always pull that out. And it's largely thread safe as long as you are using, as long as you're just putting like basic structs in, not putting things like pointers. And you can pull those out. So we can, right at the top level, generate a UID for a trace ID. And we can pop that into our context and propagate that not just within our service, but then across service boundaries and into the next service and across the next service boundary, all the way down our function chain. And then when that is received by a service, we can also execute the same middleware, pull the thing out, and apply it back into the local context within that binary. So these are both very simple. We just have a request and a response type. And we also have an error type. So in this particular case, we're responding with a particular type of error, not an error interface. And this has slightly more information, though still satisfies the error interface, which we use further up the chain. So our context is nice and simple. We have a deadline, which returns the time at which this context will cease to exist. We have a done channel, which will close when that context closes. An error, if there's been an error within the context. And arbitrary kind of key value storage, where we can store everything. So going back to our previous implementation, we can use our middleware to augment every single one as we send a request out, and then we receive it. We can pull these things back out of headers on our transport, augment them into the context locally, and then when we send another sub request, we can marshal them back into headers and then back out on the other end. And we can also send these things off. So if you had a Zipkin client, or we use a tool called Phosphor internally, we can send this information off to our various aggregation systems. So in our case, we send this just via UDP. So we'd have some block of information, like say a JSON description that we have received a request, and we just publish that, aggregate it, and persist it. And these again are open source. So we have this tool called Phosphor, and Phosphor Daemon, which is a local aggregator. And using this, we can generate pretty cool call graphs. So this is from our production infrastructure. So we are authorizing a card payment, and when we get that message in, we're going to get things like a card token from our card provider. So we can look that up, and then assuming that we get a response, we can then place a hold on the money, which authorizes the card, and then we can create a transaction in our transaction service. Now, this one was successful. In the case of failure, obviously, we're dealing with multiple distributed systems here. So technically, we could obtain a hold on someone's money and maybe not create a transaction because that might fail, in which case we need mechanisms to undo these things automatically. And while some of these things might be in process, if our process crashes as well, we need some external mechanism to also clean these things up if they haven't been correctly actioned. And this is kind of most of the systems you can get. This is all they really do for tracing. But I don't know if anyone does like publishing of events and uses event-based architectures. Like 2 people. I'm sure there's more. So we obviously want to maintain our uptime as much as possible. And that means we want to do as few things synchronously as possible. So when this request executes, this is when my card is in a terminal, or when I've just tapped it for the contactless. And we have like, I think a terminal waits for about 3 or 4 seconds. except we don't get that amount of time. When you type in your PIN and your PIN's authorized, then that message will go through various different companies in the card networks. So you'll probably go through an acquiring bank, you'll then go maybe into Visa and MasterCard's network, you'll then come out potentially into a third-party card processor, and then finally, we'll receive a HTTP request. And don't really know how long has lapsed at that point. Hopefully not long, and we have an amount of time to actually execute some database queries. And then we can do our authorization, and we respond, and that goes all the way back through the card network to the terminal, which then authorizes the card. So this needs to be as short as possible. But in order to deliver like a really immersive experience on a mobile, writing a single thing into a database isn't really the experience we want to provide. So what we actually want to do is do all sorts of asynchronous processing, which means we need to publish things onto some form of event bus. So our tracing system allows us to track asynchronous execution. So here, our wiggly line is just indicating that we published a message asynchronously. And we actually responded back to the original client, which is the card network, immediately after that. And then asynchronously, we've done things like take the card payment, look up various things like the postcode that we got from the metadata on that request. We can match that against merchants. We can do things like pull out, take the location and the data, go to the Google Places API, search for a merchant, take that, go to Foursquare, get some description of a merchant, maybe get the Twitter handle, come back, go to Twitter, get a Twitter avatar, and then put that in so that actually appears on my app. And obviously, we don't want to do all of that while your card's in a till, waiting for that to happen. Assuming that the network is perfectly reliable, which it clearly isn't, and that all of these services have 100% uptime, that's still not really something that we'd be willing to bet on happening. So we can do all of this, and we actually do a significant more asynchronous processing on that. So you do things like fraud checking. So I don't know if anyone's ever tripped like card velocity limits. Usually if you use your card like 10 or 20 times in a day, that's generally an indicator that something has gone awry. Maybe you're in a different country, which is fine, and banks should pick that up automatically. If we had the geolocation of someone's phone and we saw that they're in an airport using their card, and then 3 hours later they're in a different country, I think it's reasonable to assume they probably got on a plane. But in a lot of cases, I've done that, and my card just doesn't work when I get to the other country, and I have no way of paying for anything. So given that we can push most of this stuff away into abstractions, we can then focus on the business logic, which is building... Oh my God, seriously? Sorry, guys. We can focus on actually writing our business logic. And we can push things like provisioning and service discovery and configuration, monitoring, all of our authentication systems, and even connecting to databases off into these libraries. And we can just focus on what's important, which is clearly looking up things against Foursquare. And as far as deployment goes, Go is fantastic for this because we can statically compile our binaries. So we could either just drop them onto a machine, which I have done before. I probably wouldn't recommend that. Or we can do things like wrapping them in Docker containers. However, the default approach to this is to build your binary in a Docker container, which ends up giving you like a container that's about 600 meg or something, and then you like shunt those around, drop them onto your machine. It's extremely tedious. But there's a lot of alternative approach to that. So to start with, we can start with a scratch container, which is completely empty. Now, there's a few problems there, because by default, when you compile your Go binary with CGO enabled, you are going to dynamically link against a number of C libraries. So you can force that to be static, at which point you have a completely statically linked binary, which you can just copy into your scratch container. At which point you won't be able to make any SSL connections whatsoever, which isn't great if you're building a secure system, possibly a bank, something that people trust. So in this case, the reason for that is because your root CA files don't exist in the Scratch container. So you need to copy those in as well. And once you've done that, you end up with a container that is 10 or 20 megabytes tops. And those are obviously much easier to copy around. And in our case, we then use Marathon to deploy these onto a Mesos cluster, which allows us to deploy n number of tasks, and we can let Marathon and Mesos move those around as necessary and isolate us from individual node failures. So given that we've broken apart our application into potentially hundreds of small components, each of which is maybe running 10, 20 instances for failure isolation, and you're potentially running across multiple data centers. The main problem with microservice architectures is really the complexity as a result of that. And in any distributed system, you're going to have machines failing, network partitions, random latency spikes. And in a lot of cases, actually, things like latency spikes are a lot more dangerous. If, for example, you try and connect a memcache during a request, you expect the request to, say, take 70 milliseconds. And you connect immediately and do a read, then that's great. Or if you can't connect at all, that's also fine, because you failed fast, and you just respond with an error. But if your connection hangs because you have 100 milliseconds latency, because, I don't know, some random network partition or some latency on a network that you don't really know how it works, like a cloud network, maybe Amazon, you're going to have far more problems where you then have hanging processes which are waiting. And the most important thing you can do is have timeouts on those. So the only real way to make things like this reliable is obviously by testing. And clearly we should be testing with unit tests and some form of higher level acceptance tests. And in the case of a microservice architecture, the acceptance tests, I'd argue, are more important. Most of the failures that I've seen don't come from testing that this function works correctly, but it's actually that the interface on this thing has changed and these things aren't aware of it, and now nothing can communicate and everything is on fire. And we can test a number of different things. So we can test, obviously, load, just fire as much traffic as possible at our systems, see how much we can tolerate. And then failure testing. So Netflix have talked a lot about their chaos monkeys and their simian army, where they terminate random machines, or they apply random latency to machines. And we can check and assert that our application as a whole can tolerate these things, which, if we're running in a cloud environment, is essential. And doing that allows us to make our systems significantly stronger and more robust. If we can tolerate machines failing, then we don't need really, really expensive machines. Like, we can have commodity servers, and we can have lots of small machines, and we can just allow those to fail, and that's fine. And then on top of that, we obviously need monitoring. So generally, I would like to know if my bank is working or not before I get to a shop, put my card in, and it doesn't work. And when it doesn't work, I'd like to know why it doesn't work. So in our case, we use service discovery to register our services automatically. And then we use a health check interface. So literally a function that we execute, and we return an error and optionally some metadata. And all of our services, by using this interface, you can just anywhere in your code write some form of health check, and our health checker within the binary will publish these to our monitoring systems. And we can then check whether we've not seen any, or whether we're getting errors back. And we can correlate these with whether they're actually important errors, like not being able to connect to a database, or if they're kind of transient things that we don't actually need to worry too much about. But most importantly of all, is monitoring our business logic. And by this, I mean, if you have acceptance tests, run them in production, all the time. If your acceptance test is a definition of how your service works, so if you are logging in, you're reading people's data from a given customer, you're potentially moving money between accounts. If you have tests that do this, then why not run them in production? Because fundamentally, it doesn't matter how many servers have a full hard disk or if they're like dropping out of the network in and out. If your acceptance tests are running in production, then your customers have a perfectly fine experience. So when I worked at Halo, we did this all the time. We had a fake island in the South Pacific, and we had taxis and customers that would drive around, and they would execute every single API. And you get to a point, actually, where if that is your monitoring, you can turn off all the other things. They're not really important. They're kind of email level. This server is full, fine, it's broken now. Our other services are not connecting to it because they know it's broken. I don't need to be woken up at 3 a.m. Whereas if this happens, then everyone is going to have a bad time. If you can't use your cards, like, why are you even a bank if your cards don't work? And then on top of that, I've mentioned distributed tracing already. So if you know that something's gone wrong, then it'd be useful to be able to debug why that happened. And also you can use these to feed into your monitoring systems. So we map a reasonable percentage of our requests that go through. We record these, and then we run asynchronous analysis on this. And to give a little bit of context, this is our current kind of graph of services and the interactions between them. Obviously, this isn't a particularly useful tool for monitoring, but it indicates like the relationships between different services, and knowing whether particular connections are broken or not, and fundamentally if they're important, is extremely useful. If our card services are up, but the service that, I don't know, displays tags against transactions is down, that's kind of a different level of priority there. So why would we use Go if we were building a bank? It doesn't seem like a common choice. Not many people build banks. But there are a huge number of people who work in the financial services industries. And Go doesn't seem particularly well used, as far as I'm aware. Which seems a bit strange, because I can't think of anything better than a strongly typed, statically compiled language when you're moving money around. If anyone's used like the math-big library, being able to have arbitrary precision integers is quite useful if some country has hyperinflation, like Zimbabwe a few years ago, where the highest amount a 64-bit integer could represent was $267, because it was so many quadrillion dollars that wasn't possible anymore. But for us, it's that Go is extremely small and simple and easy to learn. So as we're recruiting people into our team, as we're growing, it's extremely quick to onboard people. On top of that, our systems are very, very heavily concurrent, and because every call goes through potentially 10, 20 different services, which are potentially on different machines, the network kind of performance and being able to do connection pooling and concurrently execute all these things is incredibly useful for us. Having said that, there are, of course, downsides. An obvious one for us is library support is sketchy sometimes, so we have to fix quite a lot of bugs in various libraries, which is fine, but if we're trying to like push forward and build a bank, fixing a bug in like a low-level database driver is not really what we want to be doing. And if we need to connect to, say, IBM WebSphere, there isn't a Go library for that. So we'd probably have to either write it, which I don't particularly fancy doing, or do that in some other language and then pipe that result through into our Go system. The other part is people starting with microservice architectures. When we started building this and we built our libraries, there wasn't really anything there. I've worked at places before where we built up libraries to do this, but there's no like Rails equivalent, or at least there wasn't when we were starting. And thankfully, that's starting to change. So as I mentioned, Peter will be doing a talk later about GoKit. There's also gRPC. And I think the fact that these things are changing is fantastic, because from my perspective, I wouldn't ever want to go back to writing one large monolithic application that I have to work with 100 other people on, and there's so much code complexity, when I could write an application that's 200 lines and deploy that, and it wouldn't affect anyone else's application. So that's about it. Thank you very much. So I think feedback's on joining. Also, if you're interested in having a debit card, which actually has a working mobile app, we'll be launching an alpha probably in the next couple of months. So sign up on our site. Any questions? No questions. One question.
Thank you very much. This is a really engaging talk. I was wondering, now that you have so much experience building such a complex system, is there anything that if you were to start now, you would do completely different?
So in my personal experience, I used to work at Halo, where we had quite a similar system. And we spent probably about 6 months developing the initial version, then another year and a half kind of iterating on it and moving things over. And yeah, I think there are definitely things that we've changed as a result of that. I think what I might change at some point is using kind of a specific message bus. So Netflix do point-to-point communication over HTTP. One of the nice things with gRPC is that it's all RPC and it's binary encoded using protobuf. So we are like halfway there. The main reason that we went that way was if you have a message bus that can route messages between things, you don't need to build service discovery on day one, which was kind of a bit of a cheat for us. But we might change that at some point. The other thing is protocol buffers, which I don't know if anyone uses extensively. So I used to use Proto 2, which I actually slightly prefer. It's more complicated, everything's a pointer, but that means you can test for field omission. Now, in our case, we have a JSON API, so if we accept protobuf through that and someone doesn't send 3 of the fields, then they'll automatically be the nil type, which is probably okay if it's a string, but if you wanted to change some description to a 0-length string, you now have no way of conveying that because you can't differentiate between not sending it and sending a blank string. Equally, if you're dealing with money, not sending a field and it suddenly being 0 is like pretty terrifying. So we use Proto 3 internally, but we've basically stuck this layer of API services which basically just marshal JSON in and out and do like corrections and stuff like that, and then fire it on in protobuf internally.
Do you have the concept of distributed transactions with commit rollback? Not maybe the classic enterprise type definition, but do you have something like that?
No. And to be honest, I'd say that's largely quite a dangerous area to get into. There's quite an interesting paper by Kyle Kingsbury and Katie McCaffrey on sagas, which I think they published earlier this year. And in that case, they are writing essentially all of the operations into a consistent store, which will then try and execute all the steps with rollback steps if they fail, and they'll retry within certain policies. The problem you have, well, with distributed transactions is you need consensus, and that obviously limits your availability. Also, you can't really do it across multiple services because there's no guarantee that some other actor in your system is obeying your, say you use a distributed lock, maybe using Zookeeper or something. There's no guarantee that another actor is obeying that. In our case, and I mean the credit card networks in particular, essentially do a two-phase commit. So we get an authorization through, and we actually do part of that within a relational database that we have transactional locking on. We then have a number of methods to make sure that that is used as infrequently as possible, so all of the other elements of our application can work even if that server's down. And then at some point, we have an asynchronous process that comes through. Say you charge X amount of money on your card, you get a settlement 2 days later, so we can confirm that. And we have cleanup processes in the background. But no, I think distributed transactions is like it's an extremely tricky area to get into. So if you can avoid it in any way, I would. Does that answer your question? Kind of.
Hi. What do you use for your integration testing?
So we just have GoTest. We have, obviously all of our unit tests are run automatically, and then we have a series of tests with like RPC helpers, which just execute calls either directly to services or to our API. We have a whole suite which match our app's behavior, and we just run GoTest to run that. When we're running it in production, we have a couple of services which we deploy. Well, they're not really services, but we have a couple of like binaries which we deploy outside of our infrastructure, which then execute these things, and they kind of keep track of the state. So you effectively have a Go routine as an individual customer, which would execute a set of operations and confirm they worked. Does that make sense? Cool. Anyone else?
First of all, great talk. Thanks for that. Just curious how extensively you use and how you found the experience of using either some sort of security SSL, for example, internally between services, for example.
Yes. So we use MQP, and we have SSL, well, TLS enabled on that. So we actually have essentially a binary to a message bus, and then off from that to the client or server, which is all TLS encrypted. What we'd ideally like to do, and what we'll be doing the next couple of weeks actually, is kind of confirming the origin. So you can imagine even if you have encryption between all of your services within your infrastructure, if you could get inside your infrastructure, you could still potentially send messages. And we need to assert that the sender of the message, one, the message hasn't been tampered with, two, we're not subject to replay attacks internally, and then three, that we can assert that the thing that sent the original message is the thing it says it is. And that's extremely difficult. Thankfully, I work with a couple of guys who are very good on cryptography, whereas I am not, or at least dangerously bad at cryptography, I think's the term. So yes, you can do things like deploying a pre-issued certificate within a Docker container, hypothetically. Personally, I don't think that really gives you much security, because if you can compromise a machine, you can pull the certificate out of the Docker container, and then you are that thing. So we're still working on kind of internal assurances there. And I don't think there's any widely accepted standard. I think a lot of companies, I'm not sure Netflix do it this way, but from what I've heard, they treat security pretty much as right at the top, and then once things are inside, like it's a bit woollier, and they don't really talk about that. Probably for obvious reasons. Like, I'm probably not going to talk about that either at some point.
Hey, Matt. I know you're busy, like, with building a bank and that, but it would be cool if you could, like, put a little example project together of these services.
Yeah, sure.
The open source sort of thing.
Yep.
Would be great to see that. You know, even with the Docker stuff, I don't know, perhaps too much, but
no, so
it'd be great to see. Yeah,
actually, now I think about it, we do have like a template service, but I think it's in a private repository. So I will change that, which literally just imports this, pre-configures the transport, and then sends messages to and from. So yeah, we can definitely do that.
How do you balance, with the microservice architecture, how do you balance latency? So in your example, you had sort of 3 hops down through
Yeah.
3 different services, possibly 3 different machines, all within this transaction where you have reasonable latency requirements. Do you ever decide maybe to make some of those microservices more monolithic to balance this? And if you have security as well, TLS
Yep.
can apply it at each.
So in the case of TLS, we shouldn't have connection overhead because we'll use connection pooling. As far as latency goes, my experience has been each one of those hops is under a millisecond. And realistically, like if you have a mobile API back to an app, as long as you're under like 50 or 100 milliseconds, you're fine. To put it in perspective from my prior experience, bearing in mind like we have 0 traffic at the moment, so we're not particularly performance sensitive. Having said that, because Go is ridiculously fast, and hops are literally a millisecond or so, like the API response times are pretty quick. Some of the stuff I've talked about before when I was at Halo, when you open the Halo app, it searches for drivers. That actually hits 20 different, roughly 20 different services, or at least the last time I worked on that system. And the response time is about 70 milliseconds. Now, some of those are really fast. For example, they need to do point and polygon checking to work out what area of London or the other cities you're in. Obviously, you don't really want to go off to a database, but the data set's extremely small, so you can just cache that in memory. The handler time in that service was 70 microseconds, and then you had a millisecond either side for network latency. So you could argue you could make it faster by smushing it all into one binary, but I'd argue 2 milliseconds is like worth the kind of break apart and like the simplicity of that. I'd argue probably most of the time if there is anything slow, you could probably cache it, and it would be generally things like databases that'll be the slow part rather than inter-service latency.
Yeah, with you guys being a bank and security and all, do you tend to write your own packages rather than using external packages? And if you use external ones, do you have a security auditing process for those?
Yes, we do.
Yeah.
So in an ideal world, I would like to not write any code. Obviously, I'm a lazy programmer. And for the vast majority of things, like popular projects that are widely peer-reviewed, are always going to be a lot more reliable than the code that I write in like a weekend or something. Things like a Cassandra driver. So we used like the widely used Go one. We then have like Halo open sourced a thing called GoCasa, which provides like some nice kind of table mechanisms on top of Cassandra. And obviously, if we want to bring those libraries in, yes, we have to vet them. We do have external security companies as well that come in, and they're like super black hat and will test us. So that's actually quite fun. They don't tell us when they're doing it. They just give us a report and say, fix these things, and don't tell us how they acquired those things. That's a lie, they do. But yeah, I think, to be honest, that applies to most things. Most libraries are simple. If you're using something that's quite complex, I think it applies, you should always be vetting that. And if you need something to be specifically, like, you can use things like GB to vendor these, which is what we do. So you can vet a particular commit, a point in time, pull it in, done. One, you have your dependencies managed, great. You don't have like backwards compatibility problems. And 2, you vetted it at that point, so you're kind of done on that. But yeah, that is super important, and that, I don't think that applies to just banking. Like, people should be wary of the code they randomly import into their binaries and deploy into production systems. Cool. I think we're done. Thank you very much, everyone.